All right. So, welcome everybody to Hoon School Live Lesson 4. Today we're going to begin learning about the very important pattern called cores. Cores are the last remaining major concept in learning Hoon. Once you understand them, you're over the hump and you're on the way to having a great understanding of the whole language. So, what exactly are cores? They're simply a pattern for you to store code as data. What do I mean by that? If you recall from the earlier lectures, Hoon compiles to knock, right? And everything in knock is just a binary tree of non-negative whole numbers, right? So if you recall, a knock formula is a pair of subject and formula. The subject is the data and the formula is the code, right? And they're both binary trees. And if you recall this from your previous homework, so you have a subject like this, 50, 51, 52, and a knock formula like 3 and 0, 2. You might reduce it by saying, oh, 3 says return 0 if the result is a cell and 1 if it's an atom. 0, 2 says grab the thing at the 2 address of this subject. So grab 50. 50 is an atom, so return 1. So with this structure that both data and code are the same kind of thing, it'd be nice to store a binary tree at some location and say, this is not like some data like 1, 2, 3 or XYZ, but it's actually a piece of code that you can pull out and run later. And this is precisely what cores allow you to do. So a core is simply a pattern to store on one side code as data, and on the other side, data as data. It's pretty much as simple as you can be. Code on the left side and data on the right side. More concretely, a core stores code in named addresses called arms, which go in the left side of the binary tree here. Then it stores the whole subject that it was built against in the right side of the binary tree here. So let's take a look at an example of making a core. So here we're making a core with this bar-sen rune. We have a single arm with lus, and we're calling it increment 100. And that's the name we're giving to this arm. And the content of the arm is .lus 100. So we're just saying take 100 and compute the next number after it. And then we close this rune with a hep because you can have an indefinite number of arms for a core. So you need to tell it when to stop reading, and that's why you close with this. I'm sorry, there's an error here. This is supposed to be bar sen, not bar hep. In general, the structure of a bar sen will look like this, right? So what happens if I take this code and run it? I can take this code and paste it in the chat for you guys. And you can try it in your dojo as well. It'll spin for a little bit. And the output will be actually kind of esoteric, actually. This. All right, so clean the dojo up so this output is a little neater. But basically, this is what returns when you type this core into the dojo. It returns a cell, and it says the first thing in the cell is 1.oks. That's just pretty printer syntax saying that there's one arm here, right? So it's storing one arm, this increment 100 arm in the left side. And because we built this against the current dojo subject, what's stored in the right side is the dojo subject. So all this stuff is a pretty printed version of what's in the Dojo subject. So let's make this a little clearer. If we pin something to the head of the subject and then we build the core, we should see it show up here, right? That'll tell us exactly what's going on. So let's pin num1 equals 1. And then let's build our core. And if we look at the output here and look at the head of it, it's actually num1 equals pat ud at the top of it. And we didn't see that here before, right? So that's saying that we pin this to the head of the Dojo subject showing up in the core. We can also do this with the tisfaz rune. If you recall, like the tisfaz rune just does the same thing, except it specifies the name of it separately. So now num2 shows up, right? And the same thing if we use the Dojo specific syntax equals num3 3. That's just Dojo specific syntax to pin something. And if we build the core, then we'll see num3 there, right? So recall that we learned the Tisgar rune. And what the Tisgar rune does is it takes a cell of, it takes two arguments, right? So the first argument is the subject, and the second argument is some code to evaluate against the subject, right? So that means if we build this core against a subject of just sig, which is just an empty subject, then actually we see 1.oks and then we see a send sig, which indicates that this right branch of the core is actually now empty because we built it against the empty subject with this, right? And the tree looks like this. Any questions on that so far? Is everything clear? All right, if there's no question, we'll keep moving on. So the arms in the core are stored as uncomputed knock. So they're not actually evaluated yet. If we recall our tree addressing, if the whole core is at the top of the tree, so at the +1 address, then the arm should be at the +2 address and the subject should be at the +3 address. So we got a question, can you explain the difference between a core and a gate? So gates are built out of cores, but we're going to get there step by step. So cores are a really flexible structure that it can evolve into all sorts of different things, and a gate is something that it can turn into, but we're going to start with the basics. So if you have a core at the top of your binary tree, so the arm should be in the +2 address, and the subject, the data should be in the +3 address, right? Based on what we just explained. So if we take our core that we just built, and then we compose it with going to the +2 address of this core. I'll type this code in the chat. Then we get this output 41100. What does that mean? That's not the result of this 101. This is actually an uncomputed knock. So what does this knock formula mean, right? Recall that knock is a pair of subject and formula. In this case, the subject is a Dojo subject, some very big thing, and the formula is 41100. So we pull out the 4. 4 means to increment the result and compute 1/100 on the subject. What does 1 mean? We haven't learned 1 yet, actually, but 1 just means throw away the subject and return what comes after the 1. So this reduces to increment 100, and then that reduces to 101. So this 41100 is indeed the knock code for increment 100. And we can also check that by running the knock, right? So if you recall the .tar rune can run knock. Oops. The first argument is the subject, and the second argument is the formula, and we get 101. So that just shows that what's stored in this arm is the raw knock code for this, not the actual result. Let's compare it though to a different method of storing increment 100. So if we do this, the tisfaz rune, that takes this computation and pins it to the head of the current subject, right? And then if we do +2, increment 100 should be stored at +2, right? Because that's what this rune does. It says take this and put it here. So if we do that, we actually get increment 100 equals 101. So there's an important difference here. When we use this rune, we computed this result and then we stored that as data at this address in the subject. Whereas here, when it was in the core, we stored some uncomputed not code in an arm of the core. So we got this 41100, remember. All right, so we can also pull out that arm of the core and just run it. So it's very simple syntax. So we just compose this core with calling increment 100 in the core. And in that case, we get 101 back. And that corresponds to this, right? So we have this core, the arm is this, the dojo subject is here, and then we call this increment 100 against this subject. Whenever we pull an arm in a core, it's called against that core as the subject. So arms and cores can refer to things in the subject as well. So consider this following code. So here we're pinning n equals 5 to the subject. And how that ends up in the core is actually it goes to the head of this subtree here. Remember, this subtree is where all the current data is stored, right? So, and this says pin to the head of the subject, and then create a core around this. So this is going to put that n equals 5 right here. This increment n, that's an arm of the core, right? Arm of the core goes on the left side, and that's stored right here. And when we're calling increment n, that's the formula we're calling against the subject, right? We have this tisgar, we're saying this is the subject, and this is what we're doing against it. We're just calling this. So what happens when we run this code? Then we get 6, right? We pinned n equals 5 and we get 6. And we can change the value of n and get a different result. Right now, n's 100 and you get 101. So any questions on that? So we're pulling an arm that was stored as data, and then we're running it right here when we run increment n. All right, if there's no questions, I'll be moving along. So cores are not eager. Yes, arms and cores are not eager. So Hoon has a lot of unique terminology, right? In a core, the left branch where you store the code is called the battery. And the right branch where you store the data is called the payload. So you can say a core is a cell of battery and payload. So it's a really common pattern to pin something to the head of the subject before declaring a core. That's exactly what we did here, right? We pinned n equals 5 to the head of the subject, and then we declared a core. In that case, the payload is further split into a cell of sample and context. So sample is just a thing at the head. And going back to this example, right? So you pin n equals 5. That's the sample. The rest of the dojo subject is the context. And the bat arm increment n. Does this graphic make sense? Why would someone want to use cores? We will learn why we want to use cores, but basically cores are the structure for any complex piece of code in Hoon. They're underneath anything, like any substantial piece of code has cores underneath it. So of course, you don't need to have cores with just a single arm, right? Here's a core with 4 arms, and you can run it. You grab the arm 4 and you return 4. Are they the Hoon equivalent to functions? The Hoon equivalent of functions is expressible using cores, but cores are more general than functions. Arms and cores can also refer to each other. So let's look at this code. Type it in the chat. So here 1 is just defined as 1. The arm 2 is actually defined as grabbing the arm 1 and incrementing it. The arm 3 is defined as grabbing the arm 2 and incrementing it. The arm 4 is defined as grabbing the arm 3 and incrementing it. So if we return 4 at the end, if we call the arm 4 at the end, then it returns 4. Right. We can even compose cores. So this is going to be kind of interesting. We can put one core in the payload or the data branch of another one, right? So let me give you guys this code. So what's going on here? This Tisgar says, with this as the subject, compute this, right? We can break it down like this, saying Tisgar, this as a subject, this core, compute the rest of this stuff. The rest of that stuff starts with a Tisgar. It says, with this as a subject, compute, grab the arm, inner core arm, right? So does it make sense to everyone how this code breaks down into this abstract syntax tree? And so what is the data structure produced by this going to look like? So it actually produces a data structure that looks like this. So this core is the outer core, and its outer core arm is here in the tree. It was computed against this as a subject. This core was in the subject. So that core goes in the payload of this core, right? That core is itself a cell of two things. It has on the left side its arm, inner core arm. On the right side, it has the rest of the Dojo subject because this was built against the Dojo subject, right? So what happens when we call this? We run this code and call inner core arm. It returns a text. This arm is a core in the payload of another core. And we can do the same thing, but call outer core arm. And then it grabs this arm, right? So we can grab both these arms. So let's take a look at this code here. We made this a little bit more complicated. So I'll post this in the chat. So instead of just returning a text, we have the same structure as before, but here inner core arm says return n, and in the same core we define n to be 2. And in this other core, outer core arm, it also says return n, and in that core we define n to be 1, right? And then this code is going to produce this data structure here. So this arm of this outer core goes here on the left. The inner core is in the payload on the right. That itself has the arms on the left and the rest of the Dojo subject. So if we run this code, what happens? We grab inner core arm and it returns 2 because this 2 is what's in scope for this inner core, right? So it runs this against this as a subject, and it sees this 2 and it returns it. So yeah, we'll get into that more, the depth first search. So what happens if we add another value for n? So even if we pin another value for n, like right before we call inner core arm, that actually just puts that n equals 10 here on the leftmost branch of the tree. And when you're calling inner core arm, it's still going to look for this most local, this n that's like in the same core as it, right? And so it doesn't even care about this n equals 10. So running this still returns 2. And we can even pin that n equals 10 at a different place. So we can pin it here. Post this in the chat. And here, what's going on here? We're saying pin n equals 10 to the head of the subject. Then against that subject, build the inner core. Set that as a subject to build the outer core, right? So that means this n equals 10 is in the payload of this inner core, in the right branch of this inner core. And if we run this code, it's still going to return n equals 2, because that's most close to it, right? But if we delete this arm n from the code, from the inner core, then what happens? So if we delete this arm n, it used to be here, but now it's gone. So what's going to happen if we call inner core arm now? Actually, this will return 10, because this says, look for n, do a depth first search starting from here, and it finds this n equals 10. And if we change that pinning back to outside, then this is actually going to fail, because it can't find a definition for n in scope. So here we moved, this used to be here, but now it's here, which puts it actually on the outermost of the tree. And when you're calling this against this core, there's no n here, so you get a failure. Why is the answer 10 not? Well, there's no addition going on anywhere. So there's no n equals 11 defined anywhere. The only values for n we had are 1, 2, and 10, right? But we deleted the one for n equals 2, this arm where we set n equals 2. So yeah. Is it possible to get n from the outer core if we call inner core? Yeah, so you would have to manually specify to run inner core arm. Yeah, let me see if I can do that. I don't know what still fails. That's a good question. I'll follow up on that later, but I think, yeah, you'd have to manually like construct, like rearrange subjects around basically. But basically, the important point here is by default, when you grab an arm, it searches the core that it's defined against for the definition. So notice we compose 2 cores here using this Tisgar rule, right? But we can even make it something even deeper. We can go arbitrarily deep with this. Let's consider this code here. So what's going on here? So we're saying, take this as a subject and build this. In that expression, take this as a subject and build this, and then build this, right? So this outermost core has a single arm called buck. And usually when a core just has a single arm, we just use this default name called buck, right? The $ symbol. And it has a value 1, right? And the second inner core has one arm with the value 2, and the most inner core has an arm with the value 3. And then that most inner core contains the rest of the Dojo subject. So recall when Hoon searches for a name in a binary tree, does a depth first search, right? And because of the way that these cores are laid out, it means that it searches all the arms in the cores for before searching the rest of the subject, right? So it's going to search here. If it doesn't find it here, then it's going to search here. Doesn't find there, then it's going to search there. And finally, it's going to search here, right? So if we run this code, it does what we expect, and it returns 1, right? Depth first search, found this, returns 1. But recall that we have this syntax where you can skip the first match of a name and skip to the second. So if you run this code, then we get 2. And we can do the same thing with 2 cats and then grab 3. Grab 3. Any questions on that? Or on anything so far? All right. So there's one more way that we can nest cores within each other. So we can put cores in each other's payloads, in each other's data, like this, right? But we can also put cores in the arms of other cores. Let's consider this code. So this core is going to build into this data structure. It has this core in an arm that's here, and that core has an inner arm. And on the right side, the payload, the data is the Dojo subject that this core was built against, right? So, but if we do this, if we run this code and call inner arm, then it's going to say find inner arm Hoon expression field. And why is that? If you recall before, we explained that exactly inner arm isn't built yet. So every arm of a core is uncomputed raw knock. So Hoon knows nothing about this inner arm until you pull it out and run it. If you pull this core and arm out and run it, then it builds this core right there. So I'll show you guys how to do that. Well, this code here. So you can do it with any of these 3 syntaxes. These are all equivalent. This third one is sugar for this second syntax. But basically we're saying set core and arm as a subject, build it, and then grab inner arm. So if we do that, then we get this text, I'm inside an unbuilt core. Well, now it's a built core, but hopefully you get the point. I'll show you guys the sugar syntax. So inner arm, core arm. So as I mentioned before, everything substantial in Hoon is a core. And if you can understand what's going on here with these cores nested inside other cores, then you're on your way to understanding the structure of any substantial Hoon program. Anything you get is going to be something like this. Are there any questions so far? And I know this is not the easiest topic, so as long as you can like give this a read, I think you guys should be able to understand it. So if we build a core, we can also modify parts of it. Yeah, ribless, that's right. That would also work because that's just the wide form of this same word. So we can also modify parts of cores. Let's consider the following. So we're pinning n equals 5 to the head of the subject. That becomes a sample, right? It's going here on the leftmost branch of the subject, right? The rest of the dojo subject is here, that's the context. And the core has a battery, which is a single arm buck, and buck contains the uncomputed code GTH N10, right? So let's just pull this arm and run it, right? So we can use this code here. This is saying set this core to the subject and then call its arm buck. And that returns if 5 is greater than 10, and that returns a no, right? 5 is not greater than 10. We can also we can give this core a name, right, and call it by its name. Using this syntax here. Here, even though this tisfaz n5 is before we define this core, it still ends up inside the core. Why is that? That's because this rune says pin something to the head of the subject and then do the following computation. And the following computation is creating the core, right? So this is still created against the subject where this is present. So it still ends up inside the core. And if you swap them, it's the same thing. These are totally equivalent. So if you run this code, right, if we just call the core GTH10, then it returns a core, right? It returns something with one arm and then the current dojo subject, right? Can we still call it with, can we still run this arm with buck? Turns out we can't. If we try to use buck to run this arm, get a find.buck. What we have to do in that case is we have to do buck.gth10. And that says, look for the name buck inside the thing named gth10. And then it runs this code. So what if we wanted to change the value of n before running this, right? So that's kind of, we're working towards something that kind of looks like a function. So let's learn a new rune for doing that. And that rune is called sentiz. So sentiz takes arguments structured like this. Its first argument is a wing of the subject. So there's something in the subject. In this case, it's going to be our core, right? We're going to put our core here. And these pairs are going to be something in this that you want to change and a new value for it. Something in this that you want to change and a new value for it. And there's indefinitely many pairs, so you got to close it with this tis. And what this whole expression will return is this thing, but with the changes made. And there's a sugar syntax for it, which looks like this. So the thing you want to change, new value for it, thing you want to change, new value for it, etc. So let's see this rune in action. I'll paste this code for you guys. So here's the two forms of it, right? We pin this core to the name GTH10, and we're saying take GTH10. In it, take n inside it and change it to 11. And this is the same thing but the sugar syntax. We're saying take this thing GTH10, inside it, take the n and change it to 11, right? These are the same thing. So what happens when we run this code? It's actually pretty boring because this code returns the core. It returns the same core. So this is what a core looks like. And we can't really tell that the sample even changed because this just says n is a pattern, right? It doesn't even tell you the value for it. But what happens, what if we try to run the buck arm now? So let's do this. Let's compose our changed core with calling the buck arm of the changed core. And now what happens? We get a send.y. Why is that? Because we change the value n to 11. And that's what this did. And this returned the new core where n has a value 11. And then we asked whether 11 is greater than 10, send.y. Right? So that's different than before. And the sugar syntax version of the same thing. Define this core GTH10, pin this to the head. In GTH10, change n to 11 with this new core as the subject, pull its buck arm and run it. Send.y. Questions on that? Yeah, so can I explain what the buck means? Right, so basically, I could have called this anything. I could have called this my arm. I could have called this GTH10 arm. I could have called this blah, blah, blah. But generally in Hoon, it's a convention that when a core only has one arm, you just call it buck. So this is just the name of the arm. That's it. And we'll use this character later. This will be useful later. So we'll learn why we have to call it buck. But basically, the convention is if you just have a single arm, you should call it just buck. Does that make sense? This is the name of the arm. So like to understand this better, let's look at buck has no special syntactic meaning. That's right. So to understand this better, let's look at another example. So so let's look at this piece of code. So we're pinning the cell A equals 1, B equals 2 to the head of the subject. Then we're building a core. That core has one arm, which grabs something named A and grabs something named B and computes whether A is greater than B. And the tree that it produces looks like this, right? So this arm is the battery, the code stored on the left side. The payload is the right side. The first thing in the payload is a cell. So instead of being here, it's split out, right? It's a cell of A equals 1 and B equals 2. And then here is the context, the rest of the Dojo subject that we built this core in, right? So if we run this code, we compose this core with calling the buck arm of this core. It returns no, right? 1 is not greater than 2. However, we can use sentis to change both values in the core and recompute it. So let's try this code here. We have a core called GTHAB. We pin 1, 2 to the head. Here's the core definition. And with that as a subject, we compose changing the core with senhep. We're saying return the core GTHAB with A changed to 5 and B changed to 3, and then grab the buck arm of that. And then we get send.y. 5 is greater than 3. And the sugar syntax version, which is a little shorter, maybe easier to read, looks like this. Find the core. We say in the core GTHAB, where we change A to 5 and B to 3, compute the buck arm. Yes, 5 is greater than 3. Any questions on that so far? All right. So as we mentioned before, this pattern where we pin something to the head of the subject and then we build a core, this is a very common pattern in Hoon. And in fact, there's a special term and a special room for this particular case. So a door is a core with a sample pinned to the head of the subject like this. And there's a special room to create a door, which is the sendCab room. So the first argument to sendCab is going to be a sample, and then the rest of it is just like how we created a core, right? We have pairs of a face for the arm, and then an arm, face for the arm, and then an arm, and so on. And you close it with this hep, right? So let's take our GTH10 core that we just wrote and write it as a door instead, using this room. It's going to look like this. So in particular, here we have sendCab, n equals pat ud, and then we have the rest of the door, right? And here, this is another way we could have wrote it with our sorry, not send bar cab, or sorry, not sendCab, yeah, bar send and bar cab. And here's the same thing we could have written in a different way, right? So we pin n to the head, and then do we remember what this rune does right here? I remember this from like lesson 2. This says take a type, pat ud, and produce an example value of it. So we're saying set n to the example value of pat ud. In this case, that is 0. So we're pinning the value n equals 0 to the head, and then we're declaring a core. These two are exactly equivalent syntaxes to each other. Does that make sense? And here's just a couple more ways you could have written it. This is also saying pin n to the bunt, the default value of pat ud. And this rune, which we haven't learned yet, is tisbar. It's just pinning n to the bunt as well. That's just a shortened way of doing this or this. So going back to our door, we can use it just the same that we used our core, right? So if we compose this door against calling the buck arm of it, then it takes this default value of 0 and returns whether 0 is greater than 10. 0 is not greater than 10, so you get a no, right? We can also mutate this door with the sentis rune that we just learned and recompute it. So let's see how we might do that. It looks pretty much just like what we just did with cores. So what do we do here? We define this door, GTH10, as a sample n, which is just set to the value 0, as an arm, which computes whether n is greater than 10. We mutated that to set n to 11. We set that as a subject, and then we grabbed the buck arm of this new core, and that says yes, 11 is greater than 10. And we could have written that in sugar syntax as well. So it's the same thing. We're defining a door, GTH10, with sample n as a number set to 0 for now. Then we're saying in GTH10, change n to 11, create that new door, put that as a subject, and run the buck arm of it. And then you get a yes, because that's saying 11 is greater than 10. So that whole process is a little complicated, right? We're approaching something that looks like a function, but it's like kind of a convoluted process to like change this value and rerun the thing, right? So in fact, we can simplify this process. There's a rune we can use to simplify this. And this rune is called sensig, So sensig takes 3 arguments. The first argument is going to be an arm. Second argument is going to be a door. And the third argument is going to be a sample value. And what it does is it grabs the arm in that door and runs it with that sample value. So let's look at what we just did and write it in a simpler way. So Daniel asks, is that a common pattern where a function always return a value if you don't specify change? Yes. So every function, every gate in Hoon is built exactly this way. So it has a default value and it'll return a value if you run it even with no input. And how we define functions are we take things, we swap them out for other things, and then we run it. So let's go back to our door. So if we look at this code I pasted in the chat, what do we do here? So we said we define GTH10 as this door, which has a sample called n, which is just set to 0 for now, and it's of type PAT-UD, right? Then we're saying take the buck arm of this door GTH10 and run it with a sample 11. And that gives you a yes, because 11 is greater than 10, right? And we could have done the same thing. Change this to 5 or 4, and we get a no. And we change this to 100, we get a yes, right? And here's the sugar syntax of it. So the only thing we change is this line right here. That corresponds to this line of code. So sig bug GTH10 11. We get a yes. We can do this with 2 values at once, right? Here we're building a door called GTH-AB. It takes as a sample 2 things. A, which is a PAT-UD, and B equals PAT-UD. And these are both going to be set to 0, right? Just because of how doors are defined. Has 1 arm, which computes whether A is greater than B. And here with this rune, we're saying, pull that arm from this door with this sample. And here's the sugar version. We're saying, pull this arm from this door with this sample. And we get a yes, right? 100 is bigger than 2. And oops, type the whole thing down. 1 is not bigger than 2. 100 is not bigger than 101. Right? Here's the sugar syntax. So that's this just corresponds to this right there. So far, we've created something that looks a lot like a basic function where you can substitute in an input and calculate an output. So this lesson, we covered the essential basics of cores and doors. And next lesson, we'll learn how to take these basic building blocks and develop any useful structure you might need, including reusable functions called the gates, functions you can call from the dojo called generators, and even recursive functions called traps, and much more. All these things can be built out of cores, and if you understand cores, you're on your way to understanding them. So I think that brings us to the end of the lesson. I have a feedback form. Solely anonymous, feel free to tell me what you like. And if you have any questions, we got about 8 minutes. Happy to take any questions. Yeah, can I explain what a door is again? Sure. So, here we define a core, right? We call this core GTH10. Then we pinned n equals 5 to the head of the subject. Then we created a core, right? That core has a single arm, which grabs n and computes whether n is greater than 10. So this structure looks like this, right? It has a battery, which is where the code is stored. The arm is stored, GTHN10, stored here. We pin n equals 5 to the head of the subject, which means if this is the whole payload, the whole data context for the core, this is going to be the left branch here, right? This n equals 5. And then the rest of the Dojo subject is here, right? So we did this using cores, right? But we can also just simplify this syntax quite a bit by using doors. So what happened is we did this. We're pinning n to be the bunt of patUD, so just the default value of patUD, and then we're creating a core, right? And that's equivalent to just using the sendcab room to create a door, saying it has a sample n, which is a patUD, and then defining some stuff. So these are just equivalent. So this is a door is a shorter way to write a core with a sample pinned to the head. Are cores in general a way to define usable code? Yes, exactly. Cores are a way that you can define code that you can run out, pull and run anytime you like. Mm-hmm. He says, I don't quite understand how having code as data does anything different. Right. So it's like, wouldn't it be simpler to just have syntax that defines a function? I'm not too sure what that means. But do you recall that like we grabbed this increment 100 arm, and this was actually the knock formula, like 41100, not the computed result 101, right? So it's stored as something different. Like it's not run yet. It's run when you want to pull it out and run it. Versus like it's like a solid already computed result. Yeah, Daniel, that's a great point. It makes it dead easy to generate new code from general rules or change existing code. Like when we ran add, right? Like this is something that's not computed yet. When we do this, we're grabbing the code for add, which is stored as data, and then we're putting it into our subject, and then we're computing it with 1 and 2 swapped in. Right. So this is a core underneath. So is mul and div and so on. I'm used from other languages where code is used separate from data. Yeah, that's it's a feature of Hoon, and it really enables a lot of powerful stuff to treat code and data as the same, just binary trees of integers. It's similar like making macros. I'm not too sure. I'm not too familiar. Thank you, Daniel. Yeah, I'll let him answer. I haven't coded in some of these languages personally. So if cores form traps, doors, etc., it seems that cores form a more general programming paradigm versus the usual function. Exactly. Cores are more general than functions. You can build functions out of them, but they are more general. And the most general way of thinking about cores is just they have code on the left side and data on the right side. And this being uncomputed is important to like this being able to become a function, right? Because you have some uncomputed stuff, you want to pull it out, swap in the arguments, and then you run it. And that's what creates a function for you in Hoon. Cool. Well, I will have these notes written up for you. You might have to give me a day or two, hopefully not 2 days, but a little bit. I'm gonna make them really clean and nice to read, and hopefully that'll help settle the idea of cores more in your head. Does Hoon support for loops? Yes, you can use cores to create recursive loops. It's not exactly a for loop because this is a functional language rather than an imperative language, but you can do the exact same thing as a for loop as you would need to do with a for loop in Hoon using cores. And we'll show you that in the next lesson. Cool. Yeah. Thank you for being here. Yeah. Cores. Once you understand cores, like I said, you're on your way to understanding all of Hoon. They're really powerful, and they underlie everything. So it's important to take a little time on this section and make sure it sinks in. And if it sinks in, then everything else will be much easier. So yeah. All right. Cool. Any last questions? And I will be at the office hours in about 15 minutes. So if you have questions on the last homework or any homework, I'll be there. I'll help you get through it. So yeah, definitely stop by if you need a hand. Yep. All right. So yep, thank you guys for being here. Cool. Look forward to seeing you next week where we will do some more work on cores and learn how to build cool stuff from them. All right.